before this conversion step. So the self-types, the constructors, if we think back to the true and false, those just get turned into basically lambdas, right? So true takes 2 arguments and throws away the second one, and false takes 2 arguments and throws away the first one. And so all the type information gets erased, and then those 2 would turn into actually that first line, the 2 constructor nodes. So true would turn into a constructor node, and false would turn into a constructor node. So I mean, runtime speed is really important for having practical programming language, and it's something we've been spending a lot of time thinking about. So I just want to give an example of sort of what interaction nets can let you do. So
are you going to give performance numbers?
Yeah. Okay. Yeah, that's the next 2 slides. So okay, so this is a modular exponentiation algorithm. You can rotate it. So if you want to compute a to the x mod n, you make an array or a tuple of the range between 0 and n. You rotate the tuple to the left, a to the x times, and you return the first element. It's a really silly algorithm. There are much better ways to do this, but it illustrates something cool about this language, because we can do this in under a second. So we can do 10 to the 10 mod 1234. We can do a tuple rotation an impossibly large number of times really quickly, because interaction nets have optimal sharing and runtime fusion. And so what happens is that if you looked at the nets that these turn into, well, we're doing what is that? It's 2 million rewrites, and there are and so then the max len is the maximum number of nodes. So this is doing a lot of creating a lot of nodes and but it's reducing them very quickly.
And so this is saying there's less than a Google number of atoms in the universe. Is it corollary?
No, because we're throwing away. So not every recursive call is actually getting. Not every rotation is actually getting executed. Okay, so they're getting fused together. Okay. So we with the result that we get this impossible seeming result that we can do a tuple rotation 10 to the 100 times. No, we're not doing that. But we can write our code as if we were doing that, and the runtime will just optimally fuse and share things that can be fused and shared. That's what the lamping optimal sharing algorithm means. That anything that can be shared will be shared. And actually, it's actually even better than this, because if we did instead of 10 to the 100, we did 10 to the 100,000. It still only takes 12 seconds on this laptop, right? Which is it's a MacBook Air. It's not the most powerful in the world, but I tried doing a Googleplex and I ran out of memory. So I mean, I think that probably.
So then, what is it that is scaling here?
What's scaling is the number. So is this this max len? It's allocating the number of nodes. And so if you try to do 10 to the it's not doing a node for every rotation, but it is scaling according to some curve. I don't know if it's polynomial or logarithmic. I didn't measure that, but that would be a good thing. That would be a good thing to figure out how this scales. Okay, so here's some benchmarks comparing Formality to other languages. And what we tried to do here, because it's really difficult to do the same function exactly in different languages, but we tried to do something as similar as possible. So these are very naive, just straightforward implementations of flipping array bits, mapping, and calling a function. Each one of these languages, so in C or in Haskell, there are ways to write it faster than the way that we did it. And there are ways to write it faster in Formality too, but we wanted to create an even playing field. So
I mean, the real question here is if this will always be faster than the way the Haskell virtual machine is doing its graph production kind of stuff.
There are cases. So I mean, just in terms of this, right? So if you try to call a function 2 to the 20 times, in Haskell it takes 45 seconds, right? And here it takes 0.1. It's the same function in both of these cases. We have a repository with these benchmarks.
Let me rephrase, like a better way to do graph rewriting would have direct implications for how fast Haskell programs can execute.
Yes, that's true. The problem with, and we've thought about writing a Haskell backend to compile the interaction nets. The problem is that because Haskell is non-terminating, we would have to have some way to account for those non-terminating terms. But if we were to, like, say, have a subset of Haskell that preserved like a terminating subset of Haskell, you could do that. It would be
That's tough.
Yeah, it would be complicated. So but we have thought about that, and I think that for things like there's a really interesting project called Grin, which is trying to use the Haskell compiler to do whole program optimization that I think has a lot of similar ideas to what we want to do. So it's a really cool project. Okay, so this is a category theory seminar, so I want to make sure I talk about categories. So we have a lot of categorical libraries in Formality. That's been mostly what I've been working on. So this is like an example of a lawful functor, and we have profunctors and contravariant. I've written like an abstract definition of a category in Formality that I'm going to show after this. It's too big to fit on a slide, but it's kind of neat. But there's a big problem. So everything I've said so far has been I think positive about Formality, but like when it comes to doing category theory in the language, I've run into a big challenge, which is that our intentional equality primitive is weak, and means that.
Well, or you need proof irrelevance.
What do you mean in terms of?
So this is something that's come up a million times in a lot of your proof assistance. What happens when you put category theory in?
Yeah.
Right. So the issue is these proofs in your category thing, right? So
yeah.
You could avoid setoids, for example, by just postulating all proofs are equal, and then that gets you around the issue for category theory.
Oh, you mean like the K axiom, like
that kind of thing.
A is equal to. Yeah, I mean you could do that, but but we want to go the other direction because the K axiom is incompatible with univalence, and so that's what.
It is a trade-off. Just
right.
Open.
So we're trying to go like down the univalent route. So yeah, I mean we could do that, but and I mean this we can right now do functors and all these categorical structures to like the same level of like safety that Haskell can, which is where you just define some functions that have the right shape and you just assume that the proofs work. But like we're really looking at trying to figure out how to have those proofs in the language, and so having basically just intentional beta-eta equality requires you to carry setoids everywhere.
This is just a side technical note you might appreciate. Like if you move to an infinity category, you might get around these issues of having used setoids at all. So that's like a third approach.
Yeah. So yes, and with the route that we're going down with, or that I'm is in, I think it's the next slide. We're trying to model our types as infinity groupoids, which is what the homotopy type theory abstraction is. But this is just so this slide is illustrating setoid hell, which is basically when you try to implement all of the category abstractions with setoids, where you're packaging in a custom equivalence relation for each of your types. You run into the problem, which is that so here with if we have the axiom of extensionality for functions, well, what equality does the axiom of extensionality use? If we use beta-eta equality, it'll work for functions over like zero order types. But then if we want to do functions of functions, if we want to do higher order functions, then like we have to have another setoid, and then every layer has to have a setoid, and it's just horrible. So what we're working on right now is basically trying to think about, okay, can Formality be a homotopical language? And it seems like we have a pretty good start. So homotopy type theory is based on mini-TT is the sort of the paper that is like these are all the prerequisites you need before you can You can do this more advanced stuff. So homotopy type theory is a way to have equality be more flexible, so that you can do this higher order. You can have the same abstractions over zero order, first order, and higher order types without having to carry pseudoids everywhere. So we have already everything that's in mini-TT, except for the fact that mini-TT is non-terminating and we're terminating, but as according to our philosophical view, that doesn't really matter because any actual implementation of mini-TT will be terminating. So in practice, if not in theory. But then the next step is adding things like higher inductive types. The extension of homotopy type theory on top of mini-TT is you need so in cubicle type theory, which is like the computational interpretation of homotopy type theory that's being actively developed right now, you need to have a couple different things. You need like an interval type, you need like a path type, you need a glue type to do composition. It's pretty complicated, but we have something already that looks pretty much like native higher inductive types, which is pretty cool because if we had native higher inductive types, we would get all the extensionality benefits without having to do more primitives. The problem is that so this is self types for an unordered pair, and it works in the sense of if we try to eliminate that unordered pair, you have to provide a proof that that the order is in fact irrelevant, but you can't actually construct the custom equality in the higher inductive type at the top level. So we're not quite there yet. If we could do that, we have a construction for an interval type and a path type that we think would be compatible with cubicle type theory, so that's sort of the edge of where our theory is. Why does all of this matter? Like why what's the actual practical relevance of all of this pretty abstract stuff? Basically, it's because people are really bad at writing software. Everyone is. This is just not an activity that the human mind is really great at. And we mess up at it all the time. And sometimes when we mess up at it, it causes huge problems, hundreds of millions of dollars, hundreds of lives. Maybe proofs wouldn't have been a silver bullet on any of these specific issues, but if we construct software with the expectation that we're going to provide safety proofs of the things that we're building, maybe that can prevent the severity or frequency of these kinds of software failures. And if we can just do that at the margin a little bit, then it's worth doing. So in blockchain, which is this project is being funded by the Ethereum Foundation in part. This is really important because blockchain is an area of software that has the combination of really small code bases, huge amounts of capital, and the platforms that they're deployed on they're immutable, so they're very difficult to change. So if we have if you have $1 million lines of code, then it makes sense to invest some fraction of that in tools or expertise that is going to make sure that those lines of code are the correct lines of code. And actually, this chart it's much worse in reality, because when I went through and measured counted the lines of code in each of these repositories, many of the lines of code are actually the same lines of code. So the ratio, so if you have an error in there's a library on Ethereum called Safe Math, which is probably correct, but I don't know if anyone's done a formal proof that it's correct. And if there was an error in it, it would take down some billions of dollars worth of smart contracts. So providing a formal proof would take probably some smart grad student or some proof theory researcher, maybe a couple weeks, and for not that much money. So it seems like the risk reward is it's just the fact that the tools are missing. So
and the limited supply of
the limit, right, right. So, well, I think it's just that most people don't know that these tools even exist. One criticism of proofs in this space is that they pass the responsibility for correctness from the implementation to the type level specification, and that's completely true. That they do that. If you get your specification wrong, then proofs don't help you. You're trying to prove the wrong thing, or you're trying to prove something different than you thought you were trying to prove. The error is is now like in your intent, right, or what you thought you were. So proofs won't help you there. But type level specifications can be much simpler than the implementations they're trying to provide safety for. So here, this is a snippet of our ERC20 token implementation. ERC20 is the most common Ethereum smart contract, and the implementations of it go hundreds of lines long. And here we have at one function from ERC20, which is called transfer, and we have some types that provide some guarantees on the correctness of that function. And it's actually really important because millions of dollars have been lost to incorrect implementations of transfer.
But
5 minutes.
Okay.
I mean, the DAO hack was like a re-entrancy kind of thing. Can
Yeah.
the programming model, rule out that kind of
Yes.
concurrency-like thing?
Yes, but it's more complicated because concurrency requires modeling like statefulness. So it's But yes, in principle.
You could rule out that kind of. Okay.
Yeah. I think Victor, my co-founder, has a blog post on using types to do exactly that. Okay, so the vision, at least for blockchain, is this idea of full stack type-driven development. Because Formality is really simple and very portable, we can run it on front end, on chain. We can run it off chain. We're writing an EVM compiler, an EWASM compiler. You can run it on a server. You can even run it in an editor, right? You can run the whole language like in Atom, and that's kind of cool. Then next steps, we're working on EVM and EWASM, working on libraries and tools. We're going to be writing Formality in itself. We're going to be exploring homotopy type theory and cubicle type theory in Formality. And then there's a lot of stuff to do on the runtime, and then some infrastructure. And then the last thing is kind of neat. If we put the type checker on a smart contract, we can create a completely trustless marketplace for code and proofs, where you can post a bounty to the first valid implementation. So here, you can say, here's, I want a bounty for a function that inverts a Boolean, or I want a bounty for a function that shows that every natural number is the sum of two primes. And I mean, if you prove that, that'd be a pretty interesting result, because people have been trying to do that for quite a while. It's Goldbach's conjecture. So that's what we're doing. The language is there. It's you can run it, you can download it. It works. We've got a whole bunch of code written in it, standard library. Yeah. So that's Formality. Any questions?
I think it's great.
Okay, cool. I think I have a tiny little bit of time, so maybe I should show the category.
Do you know what the name of the logic is? Or is it a new one that you guys?
Elementary affine logic. It's not new exactly, but
is there a categorical way to talk about it?
So here's my implementation of what a category is in Formality. So you have, objects, morphisms. You have to have an equivalence relation because of settler hell, and they have to compose. Or you have a composition function, and that composition has to be associative, and you have to have every object has to have an identity morphism.
So this example you might consider making into an infinity category. Then the
Yeah.
setoids would go away, and that's
Yeah.
Why do you need the equivalence relation?
You need the equivalence relation because you need a way to. So here, you need to show that that if you have two compositions of morphisms that are associative, you need a way to compare morphisms and show that morphisms, you need to be able to say, morphism, you need like f of g in parentheses of h, right, is the same. So if you do the composition in two different ways, right? Like I can draw this. Like you have.
You can't just say they're equal as morphisms.
Well, but there's no notion of like, if you just said that they're like.
There's like two proofs of the same. Two proofs that it's two morphisms composed the same way. Like if you had. The issue comes one level up, manipulating the proofs of associativity and the proofs of identity and such.
Yeah, so you need to be able to show that, so if you have F, G, and H, and that's G after F, and then H after G, and then this is the composition of all, so H, G, F. You need to be able to show that if you do the composition in that way, or in that way, that they're the same. Sorry, does that make sense?
Equivalence relation just
Yeah.
gives you a notion of sameness.
Right, it gives you a notion of sameness for morphisms.
For the proofs of the morphisms, of the morphism equality, I think is it no?
No, it's
I just
just
want
a notion of
to
sameness.
I just want to type MAC of MAB MAC of morphisms. I just have a type, and I just ask whether two terms of the type are equal.
Yeah. So but if you
one more level here of settings than I was expecting.
Right. So, but if you just say that they're with our primitive equality, you're just saying that they're beta eta equal, and that means that they're they have the same term level representation, which might not be true. So
representation.
Yeah.
Okay.
So if
I take the category with one object and whose morphisms are the natural numbers, where composition is given by plus.
Yeah.
Can I ask, isn't 1 plus 2 plus 3 equal to 1 plus 2 plus 3?
Yeah, so you could do that for that specific category. Oh, I think
you ran out of
better
battery.
power, maybe.
But all categories are like that, if I want them to be.
Well, suppose you had morphisms that were functions, right, for which equality might involve.
But then that equivalence relation would be somewhere else. It wouldn't be in the definition of category.
The reason you do it here is more of a programming usefulness thing, that by putting the equivalence relation in the definition category, they can all have one, and then you kind of develop.
It lets you have this definition be useful generally. I mean, I don't know. Maybe there's a way to get rid of it. I would love to be able to get rid of it.
If you do that, then what will happen is your proof now have a proof irrelevance problem. I mean, this happens over and over the first time people formalize category theory in language. Yeah, so I mean, try it. Remove the setoids, and you'll see it'll be proof irrelevance. That's the problem later.
Yeah, I don't know how I would do for the identity one. How would I show that there exists a morphism such that I know that seems like a very because that composition.
You don't ask for the one to exist. You give it as part of the data.
But the identity property is that for each object, right, that there is a morphism.
I prefer to give it as data rather than have it as property.
Okay. So.
Oh yeah.
Just like the compose function. Compose is a function you give. It's not a property. Yeah, and so is identity.
Oh, yeah. So yes, that is a better way to do identity, is to give it as compose. But it still would run into the problem of that sigma type, if you that property, you would have to show that the identity that you gave has the property that if composed with any other morphism on that object, that it returns the same thing.
Yep.
But the problem is, and the reason why I added the equivalence relation is because that compose isn't fully saturated, right? That compose has another, if you look at the type of I think, or no.
I mean, you added it for programming pragmatics reasons, and David's asking about semantics and mathematical reasons. And I think it's really just an observation.
I don't know. Well, I mean, we do say outdated, update. So I mean, so this is, So yeah, but I would love to talk about that more and figure out how to do this in a more categorically sensible way.
Mm-hmm.
This is just me translating it. And what I really want to do is I want to take So we have like a whole bunch of categorical libraries that are that I implemented like I don't know like bifunctors, right? But these are like all specialized for the category of types and functions in formality, and what I'd really love to be able to do is define a general notion of like a functor, like over any category, and then specialize it to like the category, the formality category, which I think formality like should be an actual category, unlike Haskell, where Hask is not really a category because you have a sequential operator that can break category abstraction. I think formality like should actually work because you should have the composition identity be universal over.
Maybe you can prove that by appealing to your semantics and
Yeah.
your affine logic or whatever.
Yeah, that would be really fun.
We should probably break
Yeah.
here. But,
Yeah.
but thanks.
Okay.